so let's get started. Now, before, okay, I'm just checking some of these Microsoft Teams, make sure that everything goes on. So just to make sure, can you guys see the slides on this one right now? Let me zoom in. I just want to make sure.
We can.
Okay, you can. All right, great. Thank you. So I'll quickly go over, introduce myself. So my name is Tim. I'm currently the lab TA for the EPICS program. In the past, I used to be within one of the four manufacturer teams, which is the MSc Bronze, the AT, the car team, and the vets team. Because due to the special situation for this semester, I basically has transferred to lab TA. So I think that's actually very good. I got to more experience in some of the equipment that we have in EPICS that you guys probably won't, doesn't know or don't know. I can talk about a little bit more. So right now, currently, I'm a PhD student in material science department. I do a lot of CFRP and then fiber optical sensors and some health monitoring, if that makes sense to you. But later on, I'll talk a little bit. I'll touch base a little bit more on that later on. So I do also do a lot of simulations in the scope of, yes, material selections and then 3D printing. And all of these actually are all currently kind of sort of related to my research field. And the reason why I'm bringing simulation over here is just to give you an idea that a lot of stuff you do right now, I assume it's sort of manufactured in a way, is that you can really do that in simulation side. And it really save you a lot of time. But that's under the circumstances that you know what you're doing, and you get the correct results. But I know it's always something kind of show a little bit more how fancy these kind of software can give you. So on the left hand side, that's a little drop water thing you can see, and it's hitting on the membranes. You can see on the bottom over here, this is a bullet run through into a water, and then there's sort of other stuff. So this on the upper right over here, this is basically testing a harness test. So yeah, so we have some other simulation we can actually do, and then this is basically a two flow. This is actually going into a cyclone, and then it's separating into dust. So I know definitely some of the teams that actually do with national disaster, I don't know, like disasters or like typhoons or something like that for severe weathers and stuff. So this is actually you can do. So yeah, so I was involved with MSc Bronze, which they heavily do a lot of casting, and for the past few years, they have struggled a lot of where do they want to put the nozzles in terms of melting the liquid aluminums into the mold. So you can see how I won't get into detail how this results you can interpret, but I want to kind of showcase that doing simulation is also connect to material selections and then how you do your 3D printing, because all these actually commercial package is actually free, you can download. So if you're interested, please send me an email. Okay. So getting back into today's topic about 3D printing and material selections, let's do it this way. Usually I started on the beginning, but today I want to kind of jump into the topic right now, and then hopefully you know what actually you get the most out of it for today's 50 minutes class. So yeah, so as you probably guys know that in some week during the semesters, in some way you're probably gonna submit a file called STL file, and that's usually generated from a SolidWorks or Fusion. So these software are generally free. So it's a CAP file, and then you design something, you output, and then you send it to the EPICS office, and then they 3D print it, right? But seldom do you guys know there's actually a background thing that's running, for example, how the nozzle is being printed. So to kind of step back is what I'm trying to say is that these nozzles, as you can imagine, 3D printing, you need a nozzle kind of run an X and Y and Z axis, right? And then it sort of punch the filaments out, and then you get to kind of stock it layer by layer. Which I kind of feel bad because if we're in the real classes, I'm actually able to show you the real parts where they printed. But please, be patient, stay with me. I'll try to explain clearly. And now, if you have any questions, just please jump in and then stop me and then ask me. This class is really casual, by the way. So yeah, so printing. Go ahead.
Slide. Sorry, I'm just still seeing the first slide and wasn't sure if it should be on a different slide yet.
Oh, so you're still on the, okay, yeah, good call. So that's the thing I'm always, let's do this again. There you go. So let's go to, yeah, thanks for pointing that out. Also, I'll be using the same slide for the entire 50-minute session. So can you guys see the 3D printing directions dictate the material properties? All right, thank you, yeah. So I think the biggest giveaway for this 50 minutes I want to emphasize is how you print, while you print using the nozzle, whatever the material you're extruding, the printing direction actually really matters a lot. And if you really care about your material strength, you'll be surprised how the printing directions actually will heavily influence your final parts. So I'm assuming that you want to today submit a STL file, and then you want to print something as a prototype to kind of showcase to your project partners. And for the majority cases, actually, this is a prototype, so therefore you will not use it as your final real application, right? So that's okay, it doesn't really matter. But now one thing you have to keep in note is that if you're actually using this as a testing parameters to kind of show that, okay, which material you're comparing, it really matters how the nozzle is when it's how it's printed, so the final strengths matter. So if you look at the left-hand corner over here, these are actually a dog bone coupon, and it doesn't matter, don't get away by the these shapes and stuff. What I want to show is that you can think about how, let me get my pen over here. So you can see the axis, how it is printed, okay? And down over here, basically I have a table that's being organized, and what properly over here, it's plus 45, minus 45, 090, and then so forth and so on. And what does this mean is basically you have a nozzle that's printing at a 45 and then minus 45 for all the component they're printing at, compared to 090. So 090, you can imagine X, Y axis, X and Y axis degree, and then you're printing 0, and then you're printing 90. And that's what the nozzle is basically doing, the entire process that what it is doing. Now, surprisingly, I really like this to kind of show to you guys is, at this moment, if you look at the strength over here, and if you don't know what strength it is, just think of its the highest load that it can sustain. So this number, and one of the things that we always like to see is the highest number, meaning that it has the highest resistance to fail, right? So strength, we have a 30, 32, 30, 29, 29, 29. And then there's a standard deviation of plus and minus. But over here, there's a 30 over here, right? And then what's the lowest number over here? 29. So wait, so this doesn't make sense to what we have currently learned throughout, right? So because as a material properties, they should be intrinsic properties. They should never change, assuming they are printing a PLA, right? But how is the strength of simply printing different directions, the number change? See, 30 and then 29. So therefore, I want to show is that because how it is printed, it actually really matters. So that's one thing for another. So moving forward, I want to just kind of show more evidence over here of breaking strength. So all our parts right now, we're printing polymer parts right now, right? We're not printing any metals, by the way. And then you can imagine like getting a rubber band and then you extend it very long. These has a certain range that it can stand compared to typical metals, right? So the breaking strength, meaning that the elongations as much as it can extend it. The higher the number, meaning to extend as much as it can. Actually, over here, this over here, it get 30, right? And then what's the lowest number? Actually, this is the highest number. I take that back. Sorry. So that's the highest elongation, and then the smallest one is this one over here. So actually, this is the highest, and this one is the smallest, right? So again, circling back about strength over here, that doesn't really kind of correlate any connections whatsoever, right? Because in the reality, if you have a higher yield strength, that's 30.3, you would imagine, hey, we have a higher breaking strength, meaning that it can be a little bit longer if it make, but actually it is not. This is able to elongate a little bit longer, but over here the strength is 29. That's not the highest, nor is the lowest whatsoever. So there is a lot of material, kind of material science back around over here. We can talk a little bit more, but I think I just want to like to point out is at the EPICS office in the back, there's the people they actually do this printing, and a lot of times they just put in default. I mean, they don't really like a lot of people. They don't really care. But at the end, for your project, if you're kind of aiming at, okay, you need this material to kind of, combine to something, but this is a prototype, and then you need to kind of over conquer that barrier. We can still use PLA as a material to use, but it is just how the printing direction actually give you a little bit boost, if it makes sense. So getting back into what I'm trying to say, a lot of people, at least a lot of students that I have encountered, often when I print something and then they fail, they say that, oh, PLA is not good enough. Let's change to metal. Let's do some welding, for example. Now I just want to kind of say is that no, it's just simply because printing directions. And then there's also one thing I want to point out is how much filament is being filled in the 3D printing. So you can actually print a solid material rather than, there's voids inside, something like that, airspace inside. So this is important to kind of bear that in mind. Now, getting back into the kind of material, kind of realm that I do a lot is that you can see this is a typical stress strain curve. What a stress strain curve, meaning that stress over here is just a stress as a like force divided by an area. And then strain, you can just think of an elongation. Now we have a few terminology over here, and don't worry about it. There's only one number I want to kind of point out is the yield strength, okay? So the yield strength really matter, and then a lot of people actually is concerned about this turning point over here. And why does it really matter is actually this turning point is where it starts to change from elastic to plastic. So I'm gonna put E over here and then P on the right hand side. So why does it people care? So as long as it's below this turning point of yield strength, the material will always recover by itself. It's like a rubber band, like you can, elongate. But at a certain point, if you pass that, that point, there's a certain point that it can still kind of recover, but it's not originally the length of what it is. So therefore, it is very important that whatever the material that you design, make sure that you look at its yield strength, so that when you're giving a load, it will not, whenever you're going to test it and then it's going to apply a load, that load is not going to surpass that yield strength, so that the material won't fail. The reason why I'm talking this is I'm trying to save you guys time in terms of designing, because if you already know that, okay, there's a load you're applying and that load already surpassed the yield strength, at the first point of design, you shouldn't even choose that material for your items, right? So that's something I would like you guys to take away for at least this 15-minute skill session, 15-minute skill sessions. Now, moving forward is often there's also a lot of students, they also talk about fatigue. You have a constant thing that you are giving a load on it, if that makes sense to you. It is not a concern if today you're applying a load that's lower than 75% of your yield strength. So check the material that you're currently using and look at it, go Google and check your yield strength and times 75%. That's the ball. So for example, let's use another way to explain it is, so for example, right now, I'm sitting on a table right now, right? And then I am hitting on this table right now. And then you can see, actually I cannot see myself, but you get my gestures. I'm hitting on this table right now. And then I'm constantly hitting for what, 10,000, 20,000 times. Do you, like, for your guys, current intellectual knowledge, let's say that I have a lifespan of 10 years and then I continue hitting like this. Will this table break? Let me give you an answer. No, it will not break. But this gesture I'm doing right now is a fatigue I'm doing, but the table will not break. The reason is that it has not surpassed 75% of the yield strength. Now, it does not fit to every material for 75%, but it's a rule of a thumb. So just times 75%, and if it surpassed that barrier, then you need to start doing a test of a fatigue test. And then if it's low, like this is I'm doing, don't bother, don't waste time. Okay, so that's something that if your project partners and they are sometimes very daunting, very scary, you can just tell them. Okay, so I get this kind of question a lot. So my apology, kind of jumping back and forth, but I feel in the past I'm kind of dumping you guys a lot of information. So today is kind of new strategy of teaching you guys a different way. So please bear with me. So material selections is that we have plenty of these stuff in our EPICS infantry that you can use. The few things I want to point out is over here on the y-axis, that's the Young's modulus and then the density. Now, this graph over here really help you in terms of doing design because there's always like a trade-off, like there's a constant probe. What I mean is that supposedly you're designing something for like an infant over there, like an infant. You would want to have the item to be sturdy, or is it like very light so that that toddler can carry, or something that's very sturdy that it cannot be moved. This is something that you have to kind of think about. And this diagram of here, this figure that I provide is actually very useful in terms of what material selection you want to choose at the end. So density is basically the fact that the higher number it goes, the heavier it is, and vice versa. And then Young's modulus, which is actually so there's actually a definition of here, but I'm just going to give you. So Young's modulus basically is just the stress divided by strain. You get that curve for Young's modulus. So over here, the higher Young's modulus that you have, meaning that it's resistance to failure, and then the lower it is, basically it's a lot easier to fail. So if you have higher, it's harder to break, and then lower, meaning that it's easier to break. So take foam, for example, take foam and then let's see, couple metal over here. So you can imagine, see the Young's modulus for this one is like what, like 50. The foam here where it's like 0 point-ish. So you can imagine, yeah, metal is hard to break, and then foam it's it's easy to break, right? But the trade-off is if you draw a line down over here, the metal over here, the foam over here, it's pretty light, lightweighted, right? And metal is pretty heavy, right? So you can see this basically the material train coming up, right? So why am I mentioning all these stuff, right? So you can see if you want something light, so I assume that's something like around this number, but you also want something to be high strength, that it does not break easily like foam. You basically go upon over here, right, around this region, and then around this region over here, you can see like these are polymers material, right? And then going on to over here, you have composite. Compared to metal, it's still a bit lightweighted. So this kind of circle back about current technology, especially like F-16 and F-20, and then all these commercial flights, they usually use composite. The reason why is that if you consider making metal as your is your plane, for sure it will not fly, but it will sink. So that's why when you design something for something that you need to fly, you need a lower density. So that's why composite is a open field that a lot of people do. That's something I want to kind of point out. Now over here, again, this is just kind of strengthen your memory over here. It can impact stress, strain, and then this is basically the yield point over here. So getting back into this curve over here, the yield strength, you can say yield strength of yield point. That's totally okay. Now, why I'm keep bringing up this curve is because don't be surprised, every material has different curve. Don't expect that every curve show beautiful like this, boo, and then boom. No, it's not like that. A lot of strain phenomenon can happen, and then I for sure there's tons of PhD and research dedicated their life doing this kind of research, and God, I'm not doing this. But anyway, so you can see this kind of curve, and then you get to see this kind of curve, and then you get to see this kind of curve. I don't think you can see it. So this goes forever. Well, not forever, it breaks eventually. So now, I wish we were really in a class right now, because I felt a lot of times when I'm doing this lecture, I'm talking to myself. But anyway, see, this is actually a pop quiz I want to ask you guys. So these 3 lines over here, 1, 2, 3, 1, 2, 3. Okay, so let me ask you. So if I have a metal, MET, and then we have a ceramic, God, it's like ceramic, you get what I'm talking. And then we have a polymer. I'm gonna just, for the sake of right now, I'm just gonna call POF. So we have 1, 2, 3. Now, if you have no idea what ceramic is, it's just basically your toilet seat. If you help you, kind of put memory with that. So ceramic, metal, and then polymer. Now, and then I draw a stress, and then I draw a strain. Now, quick question: 1, 2, 3. Where is this 1, 2, 3 represent for this 3 curve over here? So I'm gonna just tell you the answer. So ceramic, which is 2, is actually this one, and then metal, that's 1, and then polymer, it's way below. So does that make sense to you guys? So polymer is pretty soft, right, compared to metal and ceramic. So 3 is this curve, it elongated, very long. And then ceramic, think about your wares, dishes and stuff. Try to think of this and then drop it. It will break. It will break. So there is no elongation for ceramic material. Metals, it does. It elongated, but it's not as much as a typical polymer material. So it does elongate it. So remember that, because it also is connected to your material design. That's something that you should be aware of. Okay. So what time? So I want to also leave a few minutes for you guys to ask any questions if available. So yeah, so if I assume that majority of the students are engineering background or heading for engineering. Now if you're not, it's totally okay. Don't worry. But this is kind of showcasing to all the future engineering students. If you're going to be a future engineering, I suggest that you kind of sort of all know all these terminology, because it is kind of everybody talks about it, and then you don't want to get confused. So stress and curve, I talk about it. So strength. Now, I get the gesture is like when a lot of people talk about strength, you really have no idea what strength is. You need to clarify with whatever the project partners or the people you're talking to. What is he trying to say for strength? Is it a compressive strength, or shear strength, tensile strength, or ultimate strength, yield strength, elastic strength? So there's a different strength, and then I don't want to get you guys confused. Is that typical? A lot of people when I say strength, they're referring to tensile strength. So what tensile strength is, basically we're pulling something, right? Shear is like this, and then compression is like this. Okay. Now there are all different standard out there, ASTM standard, and then these standards usually are according to what your final application is, and then they have to comply to the ASTM standard to do their test. Or else whatever your design that you come up, it is not trustworthy to convince that your subject is going to function or work. So typically they consider ASTM as a standard and then do these variables, various tests like this. Stiffness, And then Young's modulus, hardness, toughness, elasticity, and plasticity. So these are some of the terminology you can get familiar with it. So just want to give you guys a heads up. Now, I want to bring up with toughness. So toughness is I know there's some teams, especially one of the team I was in the past, in the car team. I know there's a EPEI, and then there's is it like a speedway? So anyway, they dealt with automobiles and cars and stuff. And then one of the things is that I believe that when you design, you always would consider the fact of crashing, right? Crash, like you bump into something. So looking at this curve, a stress strain curve, which is very useful, it gives you all the information that you need so that you know that your material can survive, right? Toughness is addressing to basically impact, and what I say impact meaning like crash. So looking at these tests over here, you can see there's a beautiful color, these areas that's being colored over here. So the bottom line is that when you designing a material, you want the material to restrain from failure, which again circling back into crashing, right? So when you crash on something, you don't want the car to kind of be like pushed into like a paper sheet, right? When you crash, you still want the subject to still remain what it's originally the value it is. So therefore, we look at its below area. So let's sort of jumping back over there. So yeah, so this entire region, the bigger area you have, meaning that it can sustain crash the more as much. So meaning that it can absorb the energy. So the smaller area, meaning that it cannot. So what happens is that you have a small area. What it does is basically once it impact, and then it will stop. Gosh, I hope I was in the classroom, but I don't. So anyway, you can imagine there's something, impact, and then it all squish into like a paper sheet. But if you have a larger energy areas, it's able to sustain that damage. So the reason why I'm also talking about this is that I hope you guys at the end have questions about this. Is how are you gonna do a tensile test, or how are you gonna do all these tests? Well, come and talk to me. Then I can address where we can do the testing, right? So I can help you out. So here is circling back is be cautious about the material that you're using. What's the material? How was it made? Is it the right material that you're using? So over here, there is like sign up pyramid thing I'm showing. So this is something very important that's going to again correlate with the material science that we do a lot, and I think it kind of showcased the benefit of how we do manufacture. So over here we sort of have processing over here. I have a processing, and then a structure, and then property, and then performances. Now I hope you guys are not falling asleep right now, but really I want you guys to know that it's so important, because why am I saying? Remember when I was talking about the 3D printing, right? How the directions, like this direction, or 45-degree directions, it will change, right? So that's considered a process we'll sort of manipulate, right? So changing the process parameters, actually, it will dictate the final property as I show. So can you recall in the table, I was showing that the strength and some of the elongations, it actually changed because how the printing direction changed. So the process, so this is the property over here, right? And then if we want to have a higher performances or lower, different lower performance over here, we register performance, right? One thing I have not touched as for right now is its structure. It's a structure. So what I mean is that process, property, and performance all we're looking, but a lot of people in the neck looking at structure. So its structure is by looking, looking at microscopy and then look at structure. So then therefore we know, okay, what is the missing item? What's the missing ingredient that's so different by just changing its direction? So bear with me for a second. So supposedly today you submit a file. Okay, you submit a file to the EPICS office, right? And then these undergrad TA, they help you print out some parts. And then next week you submit the same file, and then the EPICS office print out the same thing for you. But somehow the first week the material that you that they gave you on the second week, the same material you gave you, when you test both of the material, the property is not the same, meaning that the failure is not the same. Some might, probably the first week is higher, the second week is low, the strength is not the same. And then you went back to the EPIC office and then asked them to, hey, well, what happened? What did you do? Why is it not the same? They wasn't, I don't know. So so now you can be a detective of yourself. What's the, because we know there's something changed for the property, right? But we don't know what's the process, because they don't know, and then you don't know because you were not over there looking. You don't know what 0.45. What can you do? What you can do is take these two materials and then look at the structure, because I assume these structures are completely different, right? So meaning that if you zoom in the microscopy, you can see if it's printed 0 or 45 or 90. And therefore you can justify, okay, the one that's higher is because it's printing this direction, and therefore its processing is different. So therefore we can use the structures to justify, okay, our processing was different. So these three correlations over here is so important. So you will see a lot of material science, often they go polishing, and they spend the entire day looking at microscopy to look at an image. So this is a typical metal microscopy. You can see all these little grains. And anyway, long story short is that you can see those little diagram going along, and then again, there's like research dedicate this life to study these kind of stuff. So again, this is casting. How did this pour into a mold also matters, which direction maybe. And then, all right, and then this is the polymer. So this is what I draw at the beginning, right? So you have a structure. Jesus. So this is like this. So this is like this over here. So you can see, if you look at the structure, it's kind enough to draw the structures. You see, these are the filaments, like the fibrils inside the polymer. If you don't know it, it's totally okay. But you can at least see that it's sort of different, right? When you start pulling, these lines get aligned, right? So that's why at the end of here it spike up, because when these lines are all aligned, it actually has a higher strength to do a pulling. So if you're interested, I'm more than happy to talk to you more about later. And yeah, wash your hands is important. So we still have 20-ish minutes. Let's sort of go back to the 3D printing. I hope you guys are still with me. Yeah, usually I spend 5 minutes kind of showing some very fancy YouTube video, but again, this semester special, we're skipping it. So 3D printing current out in the market. So you'd be surprised that you probably would anticipate me talking about all these like technology stuff, and then like troubleshooting about 3D printing. Now the fact is, actually I'm not going to talk about these kind of stuff. The fact is, because all these stuff you can Google and find it, and a lot of people already done a pretty good job doing this, and then they probably done better than I am. You can just Google, you can go on YouTube, and then there's tons of people doing that. However, for today's skill session, I just want to kind of point out to something that a lot of people sort of neglect to talk about, is the 3D printing current market. So if you go to Amazon right now, and then you type 3D printers and stuff, boom, there's like hundreds of lists, or well, maybe not 100, like 20-ish of like 3D printer going out over there. And then there's like so different range of prices going over there. So why am I talking about this? So I don't know, in this session right now, I assume there's some people that are first time looking into this, and then there's people that already know. Now, if you're getting into this area and then you want to kind of buy yourself a 3D printer to do a startup, kind of play around, I encourage you, please do so. Current 3D printer prices, which is at least printable and then has certain quality, is about roughly $300-ish that you can invest on, and then you can print yourself anything. However, there is also a kind of a high-end 3D printers where it can go rocketing to thousands, 2,000, 3,000s. And why there is. Now, the reason why that it is because how some of the sensors is already equipped inside, so user friendly. at the end, I'm just going to tell user-friendly. So the investment that you have input for buying a $300 3D printer, what it does is that it will do the printing eventually, but a lot of you have to do DIY. So for example, putting the filament by yourself, or if it was printing at a kludge, would it stop by itself? A lot of these low-end 3D printer, what it does is it will continue printing, and therefore you probably have to stay there all night to just look. However, some of the 3D printers up to $1,000, they are able to smart enough to detect and then therefore stop. Now, again, debatable that those investments on $300, these low ends, you can later upgrade them to a certain scale that they are able to smart enough to stop. But again, I just want to point out the pricing. Now, if you go on Google and then look all these lists over here, there is just so wide range of things. So for example, this is the list I pull out, best 3D printers, if you are focusing with me. Over here is a Prusa, and then best 3D printer under $200, Creative 3D. And then it goes on, forever and everything. So it can be very daunting at first. Again, I still go back into what your budget it is, and then what kind of later on what you would like to achieve. I am gonna bring you into what originally how I choose, and then what my goal was, and later kind of let you know how I thought about this. Again, if you have all the different thoughts, please stay a little bit longer, and then I'd love to talk to you later about it. So this is just kind of a joke is that, well, there's so many brand out there. It's like picking a car, right? There's like Ferrari, Jaguar, and then there's like Toyota, Honda, these kind of range. And it's like, I was confused. Like, which one should I choose? Maybe I should buy myself a Bentley. So originally, when I was trying to set up this 3D printers, the goal was to print a chopped carbon fiber reinforced plastic, right? So that's one thing. A lot of these 3D printers basically they print PLA. Again, PLA is just polymer. EPIC Office itself right now currently can only print PLA, but sometimes you can print ABS, but that's not what the EPIC itself. They only can print PLA. But for PLA itself, its strength is actually very low. So it's only for prototyping. And again, actually, the sad truth is that for prototyping, it's not even for prototyping. In industrial wise, when people say prototyping, they're still able to function in a certain matters to resist the force you're applying on in the reality, right? But think about this PLA when you print it, you're not going to install this on your car, is it? If it's going to install on your car, maybe it's able to sustain for one trial, second trial, but for sure it will not sustain forever and it will fail. So the true reality is for prototype, usually they're able to sustain quite some sort of passes and stuff. So therefore, it kind of driven me into printing carbon fiber reinforced plastic. Good news is that currently all the undergrad TA that's working for the EPIC itself, they're working to kind of see if they can start printing chopped carbon fiber reinforced plastic. So I'm just referring CFRP, and therefore in the future it might be able, once we're able to do that, maybe you can start printing parts and then you can really install on your equipment, and then it can sustain a little bit longer. Now, if you have any thoughts, again, feel free to stay a little bit longer. So what's your budget? So my pen over here. What's your budget, and then what dimension of your part? So in common EPICS right now, we have two Ultimaker and then one G-Max. The G-Max can print larger specimen. Now, I hope I don't offend anybody. Is when you design something and then you submit to the EPIC office, you might want to look what's the geometry it is. So just a few days ago, a person submit a STO file, which is good, all great dimension. And then when I was looking at the software, it took 8 days to print that part. And then it has to use 1.4 kg, assuming that's 5 pounds. And I was like, and then it consumed 8 days, by the way. So think about this is like, what kind of stuff can you really utterly be printing that will take 8 days? But by the way, 8 days continuously without stopping. And then it will consume 1.4 kg. So this is some kind of capacity I want you guys to be aware of. Like this 3D printer is typically a size of probably your office table, even smaller. If the part that you're designing really is something like that, perhaps there's something other material we can focus on to build your stuff rather than submitting a little small 3D printers. So anyway, what material we would like to print is something I talk about. Are you planning to modify your 3D printer later on? This is some, different, people that are interested in 3D printers, and then here I listed. So here's a fun question. We have Dremel and then Automaker. Over here I listed, this is in inches about the layer height. This is 0.004 inches, and then this is 0.3330008. So compared to the Dremel and Automaker printer, which one has a better resolution? So did I put the answers? No, I didn't put the answers. So the Automaker 2 actually has the best resolution, right? Because over here it has, the number is more smaller, right? So yeah, duh, why am I asking this question? Again, like all these has a trade-off. Like when you consider printing something this as a smaller dimension, it takes longer time. And then like at the end, like what's something that you wanna kind of balance off? Yeah, so a lot of people also, a lot of people talk about like, is it economic to build a 3D printer? Because they know it's fun, it's DIY, you get to get your hand, messy, dirty, and then you get to build something, you get happy about it. I get that. But this is another thing I want to point out is, yes, I actually try to build a 3D printer. There is a lot of online sharing data online, and then they tell you how to build it. So this is the idea what it should look like after assemble. So it take about 1 week to do this. Won't get into details. And then basically these are where you can buy all these. So basically what I'm giving you the kind of wide range right now is building from scratch, right? So basically over here I'm listing from day 1 to day 5. Where do you get the material? How much is it? So roughly it's $600 to build a 3D printer like this. It takes 1 week. So why am I talking about this is at the first of the beginning, I mentioned a typical 3D printing at the market right now, decent one. You can print something without burning your house is roughly about $300-ish. Now, I just talk about I listed right now because $600, right? So if you have kind of sense of budget and stuff, what's your thought on this right now? What I like to point out is that supposedly we invest on $300, and then folks, okay, how to step back? If my pocket right now has $600 right now, right? I wouldn't try to build my 3D printer if I have that money. I actually would buy a $300 3D printer and use the remaining $300 to upgrade that $300 machine, rather than start building a scratch with literally nothing and then spend $600 for building a 3D printer. Now, again, it depends on what actually you would like to achieve, right? So if you're like you just want to learn from ground zero and then you just want to get your home dirty and then other stuff, yeah, I get it. This is actually a true route you can consider. But again, as engineering, one thing I always felt that we neglect is about pricing. And then this is the kind of funny part is that when we were involved in these project stuff, especially in EPICS, did we ever consider cost with the project partners? Yes, we submit the budget, $200. Yes, I know. But have we ever considered the cost in commercializing stuff? I really believe it's seldom. So that's something you can be aware of. So yeah, I think we're almost running out of time. It's I think it ends on 6:20. So let's see. We still have a couple few things left. Give me like 3 minutes. So one of the stuff I want to point to you guys is that be vigilant and then be vigilant and then be suspicious. I don't know if the right word to describe is you as an engineer has to be aware of if the information is correct or wrong or does it make sense. Please do not follow whatever the people in the past or someone simply it's more senior than you and tell you to do so, and then you just follow because it might be wrong. And then at the end, it's just a painful thing. The reason I'm pointing out is if you go Google on the Amazon right now and you type 3D printed carbon fiber filament, okay? And then no, I get the gesture. If nowadays people want to print, chopped carbon fiber CFRP, it look cool, and it's fiber, it look fancy, it's lightweight and stuff. Here is a true reality. I have learned the lessons. Here's some numbers they gave. So actually, I bought this on Amazon. This was the only brand they were able to give the numbers: stiffness, flexure strength, all these numbers over here. So I bought it. I asked Jorge. By the way, if you guys don't know who Jorge is, he's the the advisor in the EPICS. So I convinced him to buy it. Yeah, great. Let's print it. All right, great. Print. All right. So over here, you can pay attention. Now I just go over with stress and curve, right? So this is just common stress and curve. Nothing changed. I just put load instead of stress, displacement instead of strain. And then we can see over here is the CFPOA, so it's a CFRP, it's different acronym. POA is the same material that the EPIC office is printing. Now you can see this curve over here. All right, let's compare which is the highest one. So these three are the highest one, right? These three highest actually is the POA. And then the three over here, that's actually the bottom one over here, right? So what does that say right now? That doesn't make sense, right? Because one would assume that printing a CFRP would have a higher strength, right? But that's not. It is not. It is actually in fact low. Then why? What's going on? Am I being deceived, or am I doing the wrong process? Doing the wrong process, huh? So this is 0 degrees. So 0 degrees is actually better over here, but just a little bit better compared to this. So just a little bit better. So this is actually POA, by the way. So, okay. So I'll leave that to you guys to kind of think about and contemplate. And hopefully I have gone through everything. Yeah, I think so. Okay. So I think basically that's all for today's skill sessions. If do you guys have any questions? You can just ask, or by the way, let me stop sharing. So let me put my email over here, and then if you just want to ask personally, although come during my office hour, I can let you know when my office hour. Then you can just come and ask questions. I'll be there in the office, if that makes sense. Okay. Questions? I see Rachel raising her hand. Oh no, you just something that's in the past. Okay, never mind. No, you're good. No worries, no worries. Okay. All right. So if you guys have no questions, I'll basically I'll let you guys go. You guys are good. Okay.
All right, thank you.
Yeah, no problem.
Thank you.
Yep.
Thank you. Have a good night.
You too.
Hi, can you hear me?